Hello guys, today I'm going to talk about a paper called Causal Representation Learning for Multiple Distributions, a General Setting. This paper has been archived in the venue of ICML 2024. To give a brief overview of this paper, it can be summarized into 3 bullet points. The first one is they leverage multiple distribution without using hard interventional data, which often considered as unrealistic setting. And secondly, they came up with a question, which is which level of identifiability can we achieve with non-parametric generating process and without hard interventional data? So what do we mean by level of identifiability is that in the literature of nonlinear ICA or causal representation learning or disentangling, people discuss about the level of identifiability, which is like how strictly we recover the underlying latent variables. It can be permutation and component-wise transformation level, or sometimes it can be just component-wise transformation level. And sometimes they group the latent variables under some existing rule and they make a clusters. So there sometimes exist cluster-wise transformation level of identifiability. So in the specific setting of this paper, they are trying to recover the level of identifiability that they can achieve. And the last point is that they show that with sparsity assumption and sufficient variability, one can recover moralized graph of true directed acyclic graph. Sparsity assumption, I'll discuss about this later part, but this is about the number of edges in the causal graph. And sufficient variability is the assumption about the auxiliary informations, which can be the distribution in this paper, or sometimes it can be just auxiliary observable variable. And this is talking about the impact of this auxiliary information implies on the latent variables changes. So now let's move on to the problem setting. Let's say our observable data is X, it is D dimension, and we assume that our true underlying latent variables are denoted as Z, which is N dimension, and we assume that D is larger than N. And one more important thing that we assume is our latent variable is modeled by SEM, which is structured equational model. So each true latent variable is a function of their parent nodes and noise and distribution. So we wrote it as Zi is equal to Fi, which gets parent of Zi, and epsilon, which is noise, and the theta, the distribution. And we assume the graph of these latent variables is directed acyclic graph. We call it DAG. This implies that the probability distribution of Z given the theta can be written as the factorized form. And the theta here is theta 1 to theta m. The m is the number of the distribution. And for example, this theta 1 includes the subnotation 1 to n, which is the latent variables dimension. And we also use the notation of mz to represent the Markov network of latent variable z. And the edge of this Markov network can be true if and only if Zi and Zj is not independent when the nodes excluding Ij are given. Okay, this is the simple problem setting. And we will talk about the neighbor. So let's assume that we are having the graph like figure here. So there's Z1 to Z5, and we particularly use notations for N for the neighbor of Zi and S for the non-neighbors, and Psi to denote intimate neighbor of Zi, where the intimate neighbor is that Zj, where J is not equal to I, and it is adjacent to Zi and all the neighbors of Zi and Mz. So to find the intimate neighbor of Zi, we first have to moralize the graph, and as I drew below, the moralized graph does not have direction, and we also have additional edges connecting Z2 and Z3. So the intimate neighbor of Zi is Z2, and the intimate neighbor of Z2 is none. And for Z3, Z2 and Z4 are Z3's intimate neighbor, and for Z4, there's none of them, and for Z5, Z4 is intimate neighbor. And there are two important equations in this paper that are important for the proofs that we are going to see later. The first one is data generating process. We often call it DGP. We have nonlinear mixing function G, which gets Z as an input and output X. And also, as I said before, Zi is a function of parent, noise, and distribution, and it follows the structure equational model. And the equation 2 is matching distribution. So what we mean by the matching distribution is that our model distribution matches the data distribution, and we can approximate X hat and zeta hat by using the model. And now there are two important assumptions. The first one is smooth and positive density. This means that the probability distribution of latent variable z is twice differentiable and positive in n-dimensional space. And the second important assumption is sufficient changes that appeared in the first part of this video. So to be specific, this means that each value of z has 2n plus the number of edge of this Markov network plus 1 different theta, which means that theta u, so there's some misnotation, this is not n but u, and which spans 1 to 2n plus the number of edges in the Markov network, such that wz comma u minus wz comma 0 with u equal to 0 to 2n plus the number of edge in the Markov network are linearly independent. And w is defined as this. I'll not go through this, but you can see how it is necessary during the proof later. From now on, we will see how can we approximate the true Markov network with several theorem and propositions. So to give a brief overview with assumptions, equation 1 and 2, which are data generating process and matching distribution, are needed to the most of the proposition and theorem. And also theorem 1, 2, 3 are depending on the sparsity assumption, which are the condition about minimal number of edges. And some others depend on other trivial assumptions or almost no assumptions, which can be lemma 7, proposition 3, lemma 1, and proposition 2, and etc. And also, it is an overview of the relation of the lemma in theorem and propositions. This looks quite complicated, so we'll go through one by one. We will start from proposition 1 and theorem 2 and to theorem 1, and then proposition 3, proposition 4, and then theorem 3. Okay, the first one, the proposition 1, assumes assumption 1 and 2, and we suppose that our data generating process follows the equation 1, and we can learn x hat and zeta hat that matches the distribution of theta. Then, given that zk hat and zl hat, which are not adjacent, the following equation is equal to 0. And also given that zk hat and zl hat, which are not adjacent, and if zi and zj are adjacent in the Markov network, the true Markov network, this equation is equal to 0. So we'll see the brief overview of the proof. We started from the cross derivation is equal to 0. We differentiate log of pz hat twice, one time with zk hat and one time with zl hat. And if we consider the Jacobian matrix, which transfer from z hat to z, the pz hat given zeta hat multiplied by the determinant of inverse Jacobian is equal to pz conditioned on zeta. By using this, we actually calculated the second derivation. The equation looks quite complicated, but you can see the notations on the right upper side of this page. There's eta and eta prime and eta double prime, h prime and h double prime each. And since we knew that the cross derivation should be 0, the following equation is also 0, while u spans 1 to 2n plus the number of edges in the Markov network. And here, we leverage the fact that this equation is true, which is about the eta double prime. And by using assumption 2, we concluded that the proposition 1 here in the previous slide is true. This is a brief overview of the process of the proof, but if you need more detail, you can refer to this paper. And now let's see theorem 2. Theorem 2 also need assumption 1 and 2, and equation 1 and 2, and also the sparsity assumption. Then the Markov network of recovered Z, which is Z hat, is isomorphic to MZ, the true Markov network. To prove this, we need lemma 2 and 6. Lemma 2 is that for any invertible matrix A, there exists a permutation of its columns such that the diagonal entries of the resulting matrix are non-zero. And lemma 6 is that if Zi and Zj are adjacent in the Markov network Mz over Z, then Z pi I hat and Z pi j hat are adjacent in the Markov network Mz hat over Z hat. And this lemma 6 indicates that the number of edges in the recovered Markov network is always equal or greater than that of the true Markov network. So how do we use these lemma and the proposition 1 that we have seen before are used in the proof of theorem 2? So first we define V is G inverse dot G hat. It means that the function V maps the learned latent space to the true latent space. And we assume that this V is the theomorphism. And by using lemma 2 here, we can conclude that there are pi such that the derivation like this is not equal to 0. where I spans from 1 to n. And also, if we suppose that the ith latent and jth latent in the true Markov network are adjacent, but the z hat pi I and z hat pi j are not adjacent. By using proposition 1, we know that this multiplication of two derivation is equal to 0. And the left equation and the right equation contradicts each other. So it is true that if two nodes in the true Markov network are adjacent, the recovered one is also adjacent. And in the next slide, here we talk about the number of edges. And as I told before, because of lemma 6, the edges in the learned Markov network is always greater or equal to the number of edges in the true Markov network. But by considering equation 2, the number of edges in the learned Markov network is always smaller or equal to that of the true Markov networks, which means that they have same number of edges and they are isomorphic. So we finished the proof of theorem 2. And now let's move on to theorem 1. Theorem 1 also requires assumption 1 and 2, and they follow equation 1 and 2, and it also assumes sparsity. Then, if we suppose that zk hat and zl hat are not adjacent, each zi is a function of at most one of zk hat and zl hat, and also for each pair of adjacent nodes in the true Markov network, at most one of them is function of zk hat. The process of proof is a bit complicated, but let's see the proof sketch briefly. So first, by using proposition 1, we know that multiplication of these two terms are 0. And because of this, we can redefine our goal. We have to show that zi differentiated by z hat k is not equal to 0 for some value in z hat. Then derivation of zi regarding zl hat is equal 0 for all values in z hat. And we knew that by theorem 2, there is permutation pi that satisfy the isomorphic relation to the true Markov network, and we suppose that z pi I hat and z pi k hat are not adjacent. Since we are gonna prove theorem 1 by contradiction, we suppose that there is a situation that these two equations are both not 0, and let's define phi z hat is equal to this equation, and given the supposition, they put value of z hat 1 and z hat 2 each and use intermediate value theorem, and we can conclude that there are z hat 3 exists such that can make the phi z hat equal to 0. However, since derivation of z over z hat when putting z hat 3 to z hat is not invertible, it means that it is not diffeomorphism, which is contradiction. Now let's move on to the proposition 3. Let's suppose that zj is not adjacent to zi and also the neighbor of zi excludes zj. And if aij is equal to 0, then the inverse of aij is also 0. So this is proposition 3. And A is the adjacency matrix of the Markov network. Here we also assume that this A is n by n, it is invertible. We use lemma 7 to prove proposition 3. Lemma 7 is if A is an n by n invertible matrix, it can be expressed as a linear combination of the power of A, like the equation below. And because of this, now we have to show if aij is equal to 0 and the power of aij is also 0. Then we can conclude that proposition 3 is true. So first we will show if aij power of k is equal to 0, then aij power of k plus 1 is also 0. And then we want to prove by contradiction, which means that we are supposing that aij power of k plus 1 is not equal to 0 and zj is not adjacent to zi and neighbor of zi excludes zj. And this assumption implies that zj is either not adjacent to zi in Markov network or there exists zl in the neighbor excludes zj, such that zj and zl are not adjacent in the Markov network. And here, as you can see, we can rewrite the power of k plus 1 into the multiplication of these two terms. The assumption that we gave implies that there must exist m such that the multiplication of aim power of k and amj is not equal to 0, which means that both are not 0. And since both a power of k and a satisfies the property, this indicates that zm is adjacent to zi and all nodes in the neighbor of zi excluding zm, and zj is adjacent to zm and all nodes in the neighbor of zm excluding zj. And now we can consider two cases, whether m is equal to L or not. And if m is L, it contradicts the case A. And if m is not equal to L, it contradicts the case B. So we have shown that the proposition 3 is true. Now let's move on to the proposition 4. Proposition 4 also needs assumption 1 and 2, and it satisfies equation 1 and 2, and it needs sparsity assumption. Then there exists the permutation pi of estimated latent variables denoted as z hat pi, such that each the latent value in z hat pi is solely a function of subset of union of zi and the intimate neighbor of zi. We'll see the sketch of proof briefly. Step 1, we just consider the simpler case. We are going to show that zi is solely a function of z pi I hat and subset of z pi r hat, where zr is the element in the intimate neighbor of zi. To prove this, we first leverage theorem 2, which denotes that there is a permutation pi such that del zi by del z pi I hat is not equal to 0. So clearly zi is function of z pi I hat. And then next thing to prove is that if zj is not adjacent to zi, then zi cannot be a function of z pi j hat. And to prove this, let's suppose that zi and zj are not adjacent, then z pi I hat and z pi j hat is also not adjacent. By theorem 1, zi is at most function of one of z pi I hat and z pi j hat, which means that zi cannot be a function of z pi j hat. And now to refine the step 1, we suppose that zj is adjacent to zi but not adjacent to some zk which is in neighbor of zi excluding zj. Since we have shown that the Markov network of true latent variable and Markov network of z pi hat is isomorphic, z pi j hat is not adjacent to z pi k hat. And by using theorem 1, at most one of them is function of z pi j hat and z pi k hat, we can say that zi cannot be a function of z pi j hat because zk is a function of z pi k hat. Hence zi is function of z pi I and z pi r hat, where zr is the element in intimate neighbor of zi. And step 2, we consider zl, which is not in the union of zi and intimate neighbor. And since zi is not a function of z pi l hat, del z by del z pi hat with subscript of il is equal to 0. And here, by using proposition 3, we know that inverse of that is also equal to 0, which implies that del z pi I hat over del zl is equal to 0. So we have proved proposition 4. And by using lemma 4, 5, and proposition 4 and lemma 2, we can now finally see theorem 3. Theorem 3 also needs assumption 1 and 2 that satisfies equation 1 and 2 and also needs sparsity. Then there is permutation pi such that z pi I hat is solely a function of zi and subset of intimate neighbor of zi. To see the flow of proof of theorem 3, we have to see lemma 4 and 5 first. Lemma 4 denotes that given Markov network over variable z, if we say n is neighbor and psi is the intimate neighbor, then for each I not equal to j, we have ci in the intimate neighbor of zj, if and only if the union of zj and neighbor of zj is a subset of union of zi and the neighbor of zi. We will omit the proof. If you are interested in, you can refer to the original paper. And lemma 5 denotes that if the union of zi and neighbor of zi is equal to union of zj and neighbor of zj, where I is not equal to j, then we have equal nodes in the union of zi and intimate neighbor of zi and union of zj and intimate neighbor of zj. Now let's see the proof of theorem 3. We first leverage proposition 4 to use the fact that there's a permutation sigma exists such that z sigma I hat is solely a function of a subset of union of zi and intimate neighbor of zi. And by using lemma 2, there's a pi exists that diagonal entries of Jacobian are non-zero. And here are two cases. If pi I is equal to sigma I, which is trivial permutation, z pi I hat is function of ci because of lemma 2. And also we have del pi I hat by del z is equal to del pi sigma I hat by del z, which indicates that z pi I hat is solely a function of zi and a subset of intimate neighbor of zi. And the second case is non-trivial permutation, which means that pi I is not equal to sigma I. In this case, by using lemma 4 and lemma 5, z sigma jk hat is solely a function of union of zi and intimate neighbor of zi. And since we have pi I is equal to sigma jk, z pi I hat is solely a function of subset of union of zi and intimate neighbor of zi. And furthermore, we show that z pi I hat is a function of zi. Therefore, z pi I hat is solely a function of zi and a subset of intimate neighbor of zi. So until now, we have shown the identifiability of the Markov network, and to connect this with causal structure, previous works incorporated faithfulness assumption. However, people consider this faithfulness assumption is somewhat unrealistic. So the authors provide two weaker assumptions, which is SAF and SUCF. Let's see one by one. So the assumption of single adjacency faithfulness is that in the given directed acyclic graph, if Zi and Zj are adjacent in the graph, then Zi and Zj are not conditionally independent when given all the other nodes. Probably this is not K but J. And the second one is single unshielded collider faithfulness assumption. We also assume that there's a latent causal graph G, and if Zj is collider and having parents Zi and Zk, and it is unshielded collider, then Zi and Zk are not conditionally independent given the other nodes. So by using two weaker assumptions, SAF and SUCF, we are now going to talk about the relation between moralized graph and the Markov network. So in the general setting, given the latent causal graph G and the Markov network M, the undirected graph defined by the Markov network is always a subgraph of the moralized graph of the true causal DAG. However, by using SAF and SUCF, we can achieve stronger identifiability of the network, which is that the undirected graph defined by M and the moralized graph of the causal graph G are the same if and only if the SAF assumption and SUCF assumptions are satisfied. Finally, we will see the model briefly. They use VAE architecture to implement their causal representation learning model. So they leverage the elbow loss, which is commonly used, and it consists of the KL divergency and the expectation of log probability of X given Z and Z ahead. So in the KL divergency, we can see there is prior distribution. To approximate this prior, they use normalizing flow to mimic the inverse of latent structure equational model. This is kind of commonly adopted technique in the causal representation learning. So if we see the equation, the noise epsilon I hat and the log of determinant of the conditional flow transformation on Zi are coming from the flow network, where NN here represent the neural network. To recap, we make an assumption on the noise term epsilon that it follows independent prior distribution. And if you modify the equation above, the prior distribution can be written as the equation below. And so we just saw the non-parametric implementation of prior, but they also suggest the parametric implementation, which assume data generating process with scaling and shipping. So they manually wrote the equation, as you can see here, and by reorganize the equation, we can write the equation with respect to the epsilon hat, like the previous one, like here. And also we can write the log prior, as you can see here. Since we also assume sparsity, there's a constraint on the number of edges, which is L sparsity here. And this L sparsity is just a norm of the adjacency matrix A. So this is the end of the video, and thank you for listening.